So welcome back to science class, and we were talking about sound, right? So here are the topics we had covered so far, and in the last class we have found out what is the speed of sound, right? What is the formula for the speed of sound? And if you can recall, we have found out that speed of sound in air was 340 meters per second. So in this class we will learn about speed of sound in different media, reflection of sound, and mainly we will focus on these two topics in this class, and later on we will take up the range of hearing, applications of ultrasound, and in the end the structure of human ear. So let us start off with speed of sound in different media. And under this topic we will learn about the speed of sounds in different kinds of things like solids, liquids and gases, right? We will see what is the speed of sound in these different medias. We will not actually find out the values, but we will find out in which medium does sound travel the fastest. So if we are just directly finding out the speed in all this kind of matter, we will actually end up with different kinds of values, and finding these values is not at all easy. So to compare, it is better to have a qualitative analysis, right? So we will do that using a different example. We will do the qualitative analysis by using the whisper game concept. So let us learn what is it. So according to the whisper game, imagine we have a group of children. We have a group of children standing in a line, in a straight line, and the objective of the game is to pass on the whisper to the next person, right? And one more rule is there: communicating loudly is not allowed. Now the game starts. The first child hears a whisper and tries to pass it on to the next child. So you are getting the game, I think. The first child hears the whisper and then passes on the whisper to the corresponding to his corresponding friends, right? So let us consider different spacing between all these friends, right? First, let us consider all of the children standing close together. All of them are standing close together, right, after one another. So when they are whispering, whisper can be communicated very easily, right? Whisper can be communicated very easily because they are just standing one after another, and they will have to just turn their heads and whisper it to the other person's ear, right? So in this way, whisper can be communicated very easily. And in other words, we can say the whisper travels fast. Now let us imagine these children as the molecules in the matter. Let us imagine these children as the molecules in the matter. When molecules are close to each other, if one particle receives the vibration, one particle receives the sound vibration, it is very easy for that particle to transfer that vibration to the corresponding particles, right? And in which matter are the particles close together? They are in solids, right? So in solids, the vibrations can be transferred very easily, and it can be explained very easily through this concept. Let us consider the second case. The children are now standing at an interval or a gap of 2 meters, right? So now Whisper can be communicated after traveling a distance of 2 meters. Right? Whisper can be communicated after traveling a distance of 2 meters. So you can see, if I want to transfer my whisper to the next person, what will happen? I have to first travel 2 meters and then pass on the whisper. So it is consuming a bit more time, right, than the earlier process, because my friends are a bit apart from me, are a bit far from me. Or in other words, we can say the whisper here travels at a slower rate. The whisper travels at a slower rate, right, because all the friends are far apart. And here let us again compare them to particles of matter. Let us compare them to the particles in liquids, as they are only a bit far apart than in case of solids, right? So let us compare them with the particles in liquid or the molecules in liquid. If one particle in a liquid receives the vibration, it has to travel a certain amount of gap, right? They have to cover the gap, and then only they can pass the vibration on to the next particle, right? First, one particle has to cover the gap which is in between the two particles, then only they can pass on the vibration to the next particle. So you can see, we can compare whisper with the vibration, right? We can compare whisper with the vibration, the traveling of the vibration. So as the whisper in this case travels in a slower rate, so we can say that the vibrations in case of a liquid also must travel at a slower rate than in case of solids. Let us consider the final case when they are standing very far apart. You can see they are standing at a distance of 20 meters. It is very far off, right? Just to pass on a whisper. So in this case, whisper can be only communicated after traveling a long distance of 20 meters. Whisper can be communicated after traveling a long distance of 20 meters. Or you can say whisper travels at a much slower rate than the earlier one. And of course you can compare now this concept with the gaseous molecules. Compare these children with the molecules of gas. In gas, the molecules are spaced very far apart, right? So when one molecule receives the vibration, it is difficult for it to pass on to the next molecule, because it has to travel that gap, right? It has to cover that gap between the two molecules, and then only it can pass on the vibration to the next molecule, right? So you can see one thing, as the distance between the children increases, the rate of transfer of whisper decreases. Or in case of the states of matter, as the spacing between the particles increases, the speed of traveling of a wave or the speed of traveling of a vibration slows down, right? So you can see, if the molecules are close together, it is very easy to pass on the vibrations onto the next molecules, which is a bit difficult in case of the liquid molecules, which are spaced a bit apart, but it is the most difficult in all the three cases to pass on the vibration in gaseous molecules, because they are placed at a very far gap, right? So ultimately we get the speed of sound, which is nothing but a vibration only, right? Sound is nothing but the vibration of air column, or the wave which is created due to the vibration in the air column. So the speed of sound must be the greatest in solids, and then in liquids, and then in gas, because Sound can be transferred to the consecutive molecules very easily in case of solids than in liquids than in gases, right? In gases, sound vibrations can be transferred in the least effective way. And you can try a few experiments to find out this. That, for example, if you try to hear the sound of your friend tapping on the table, right? If you try to hear the sound of your friend tapping on the table by keeping your ear on the table, right? You are keeping your ear on the table and your friend is tapping on the other end of the table, you will actually hear two sounds, one through the air, one through the table, right? You will hear two sounds, but one thing you will notice that the sound coming through the table is louder than the sound coming through the air, right? And why is it so? Because the speed of sound is lower in case of air and speed of sound is greater in case of solids like the table, right? And in a very small amount of time you are getting more sound energy to your ear through the table than through the air, right? Because as the speed is low, the transfer of sound energy will be low. Similarly, through the table, as the speed of sound is high, transfer of sound energy will be higher, and we are actually getting more sound energy through the table, and it is giving us a louder sound. There is one more example. Sound of a train can be heard very easily by placing your ear on the railway track, even when the train can't be seen or heard through air. When you place your ear on the railway track, you can easily hear that the train is coming. You can easily hear the sound of the wheels, right? But at that time, it may happen that you are not able to see the train through air, means you are not being able to see the train actually or hearing the train, right? But you can actually listen to the sound coming through the railway tracks, which is traveling faster, and can say easily that the train is coming or not. But this experiment is actually not very good, and you should not try this because you never know when the train is coming. Trains are very fast, and it is actually not good to go near the railway tracks. It is very hazardous. So let's come to the next topic, the reflection of sound. Sound bounces off a solid or a liquid like a rubber ball, and it just reflects in the same fashion as light does. Sound can reflect in the same fashion as light does, right? When light falls on something, it gets reflected back, and in a similar fashion, when sound falls on any particular obstruction, it reflects back. And you must also know that the laws of reflection for light is also true for sound also. Or in other words, we can say the angle of incidence and the angle of reflection are the same, and the incidence sound wave and the reflected sound wave and the normal all lie on the same plane. And you can try this with an experiment. So what we have done, we have placed a soft wood, and on both the sides we have placed cardboard tubes through which sound can travel. And why have we placed this soft wood in the center? So that sound does not travel directly, so that we cannot hear this clock directly on this side. So this arrangement is made, and you will actually observe by placing your ear on this cardboard tube, the second cardboard tube, you will actually hear the clock ticking. You will hear the clock ticking. Now sound is not traveling through the softwood, right? That is why we have kept the softwood. We have kept the softwood so that sound does not travel directly. So in this case, the stopwatch sound travels through this cardboard tube. The sound travels through this cardboard tube, hits this wooden board and gets reflected and passes through the second cardboard tube. And when we place our ear with the cardboard tube, we can actually hear the sound. And this experiment proves that sound actually gets reflected. And here also you can see angle of incidence and angle of reflection is marked, and according to the laws of reflection, both these angles must be equal as well. So let us see different applications of the reflection of sound. Major applications are megaphone or horns. In these equipments actually the sound gets amplified. And how does it happen? When sound waves come from our mouth through the small hole in the microphone or the megaphone, right? What happens? The angular waves waves can come in any direction, right, out of our mouth. It is actually a wave, so it's just spread in all directions. So whichever waves are coming at an angle, what happens? They get reflected and reflected over and over again. And you can see, if we trace these waves, their amplitude has increased, right? Their amplitude has increased. And therefore you can easily say that these megaphones actually increase the loudness of sound, right? They have increased the loudness of sound just through constant reflections of sounds. And for the horn also it occurs the same way, and this round part actually gives a more longer path for sound to get reflected over and over again. And this horn follows the same principle as this megaphone. The sound gets reflected and reflected over and over again and comes out through the bigger opening. One more application is in the field of medicine, and you might have seen doctors use these equipments called the stethoscope, right? And using these instruments actually they are able to hear your heartbeat, right? Using these instruments called stethoscope, they actually are able to hear the heartbeats. And how does sound travel through these thin tubes? When your heartbeat is coming through one end of the tube, suppose your heartbeat comes from this end of the tube, which is this end, which looks like a dial. What happens? The sound waves get reflected over and over again, as it is shown here. The sound waves get reflected over and over again, and ultimately they reach both the earpieces, right? That means whenever the doctor puts the dial on your chest, the sound of your heartbeat gets reflected over and over again through that thin pipe. It gets diverted at the junction and reaches to his earpieces, and in this simple way he can easily hear your heartbeat. And one more application is in case of auditorium halls. In auditorium halls actually what happens, in this at the stage actually at one end of the auditorium hall someone speaks, right? Someone speaks, and the speakers are mainly kept just beside that stage. Now obviously the person sitting in the first row will be able to hear the things going on the stage better, right? They will be able to hear them better than the audiences which are at the back of the seats, right? Which are at the back. So what is done? The ceiling of the auditorium is made curved. the ceiling of the auditorium is made curved, and what happens? Whatever the sound is coming, they get reflected from the ceiling and they travel towards the back. As you can see here, the sound which is originating from the stage at this point gets reflected over and over again. You can see one of the sound waves get reflected and comes to the audience at the first row, one of it goes to the second row, and some of it go to the last row, right? And this is how sound can be spreaded evenly within the auditorium hall, and due to this, everyone in the auditorium can hear what is going on the stage very easily. And this kind of curved ceiling is actually termed as soundboard. This kind of curved thing actually acts as a reflecting surface, as you have seen in case of mirrors, right? They actually act similarly as a concave mirror. They act in a similar way as a concave mirror, and if the source of sound is there, the sound hits the reflecting surface and goes back, right? And here you can see the source of sound is placed at the focus of the soundboard. The source of sound has been placed at the focus of this soundboard. And what happens? If something is placed at the focus of a reflecting surface, the rays coming out from it, or the waves coming out from it, gets reflected and becomes parallel to the principal axis, right? What you have learned in case of light. The rays come out from the focus and becomes parallel to the principal axis, and here also the same thing is occurring with sound waves. And as you know, the reflection of sound is of course the same as that of the light. So one of the applications we have learned, soundboard. So let's learn about a new word which is called echo, and it is actually not a new word. I think you have heard it many times. Echo. You hear an echo when you just speak out loud when you are in a hill station, right? When you are in a hill station, you speak out loud, and whatever you have said, it comes back as a reflected wave. You can hear what you have said over and over again, right? And the sound fades off gradually. So what is an echo? The repetition of sound waves caused by their reflections is called an echo. You can see if a person claps and if a wall is there, the sound hits it and reflects back, and the person can hear the sound of his clapping once again. And this repetition of sound is called as an echo. Now you don't hear an echo in your room, right? And why is it so? Echo actually requires some specific gap between you and the source of reflection, and there must be also a specific time gap between your source sound which you are speaking and what you are hearing as the reflected sound. There must be a specific time gap between these two. We can hear the original sound and the reflected sound, which is the echo, separately only if there is a time gap of at least 0.1 second between them. Whenever there is a time gap of 0.1 second in between them, like when I am speaking and I hear my reflected sound after 0.1 second, then only we can differentiate between our sound and the echo. And if the time gap is less than that, our ear actually hears both the words as the same. If the time gap between our source sound and the reflected sound is less than 0.1 second, we cannot hear them as different sound, and our ear makes it out as a single sound. So the least time gap will be 0.1 second, and the time gap can be more than this. So let us find out what is the minimum distance to hear an echo. Let us consider that we are standing in front of a wall spaced at a distance d, and we are shouting hello. As you can see, we are shouting hello, and this sound gets reflected from the wall and comes back to us, and we are trying to find out the distance d such that we hear an echo, right? So let us try to find out. From your earlier class, you have known that speed of sound in air, as we are talking about air in this case, the speed of sound in air is 340 meters per second, right? Now, distance traveled by the sound will be speed into time, right? We know what is the speed of sound, right? And the time required to hear an echo was 0.1 second. And here we are trying to find out the distance required for hearing an echo only, the minimum amount, right? So here we should take the minimum time as well. Speed into the minimum time to hear an echo will give us the minimum distance to hear an echo, right? So let us put the respective values. And by putting these values, we get the distance traveled by sound to make us hear an echo must be 34 meters. Or how much distance is the sound traveling in this 0.1 second? Sound is traveling to the wall, right? It is hitting the wall and coming back to make us hear the echo, right? The sound is hitting the wall and coming back to make us hear the echo. And this time gap, when we are speaking and we are hearing the echo, was 0.1 second. And you can see in the 0.1 second the sound has traveled the minimum distance twice, right? So this distance must be twice of the minimum gap which we require to hear the echo. So the d which is given here must be this minimum gap divided by 2, right? So distance between me and the wall must be 34 by 2, which is 17 meters. So you can see the minimum distance to hear an echo must be 17 meters, right? And this is actually the minimum one, and the distance can be greater than this, right? And you can also apply this law when you are in a hill station and shouting, and when you are actually among the hills, when you are shouting and you are hearing an echo, you will actually find out, if you approximate, the distance is more than 17 meters. So in this class we have learnt about the speed of sound in different mediums, right? Like in solid it is the fastest, and it is followed by liquids, and the least speed in gases, right? And then we have learnt about the reflection of sound, and it follows the same laws as that in the reflection of light. And finally we learnt about echo. So for better understanding of these topics, you can always log into WebCoach. You can also follow your school textbook, and NCERT books are a must. And for further practice, you can always go for the TMH group. So thank you and see you again.